Alright, so our next topic to talk about dimensional analysis is the Buckingham Pi theorem, which is something that we can actually derive, and we'll do this in class. We'll talk this through. You can derive it from concepts of linear algebra the way we already have, which helps you count up. But for this little video, I'm just going to talk about the counting up and what it is we're counting and the result we're expecting to find using a simple example, which is the speed of a boat in water. I'm actually going to do a little bit slightly more complicated version than the one in the notes, because why not, and giving us one more parameter to think about. Okay, here we go. So the concept of Buckingham Pi is that you're counting the number of parameters in a problem, the number of results that you're looking for out of the problem, and the number of fundamental dimensions that can be used to describe all of the dimensions of those parameters and results. So you can do this. Here's the amazing part. You can do this even when you don't know the equation of motion or anything like that. You just know some of the parameters that you think are going to be important. Okay, so here's our boat. It's traveling on the water. The boat velocity is what we're interested in, u. Or I guess it's the boat speed, really. Boat speed is what we're interested in, u. We have the length of the boat. We can also think about the height of the boat, the area, the surface area, wetted area of the boat, all kinds of things like that. But let's just keep it simple, have just the length of the boat. Now there's some other parameters floating around, like you might have the speed of sound in water, you might have the viscosity of the water, you might have the acceleration of gravity. This last one is maybe not so obvious unless you've done gravity wave problems before, but the wave speed of waves on the surface of the water has a lot to do with the acceleration of gravity, so keep that in. Okay, so these square brackets say take that parameter and tell me what the dimensions of it are. So c, the speed of sound, is a speed, so its dimensions are length per time. The acceleration of gravity, length per time squared. The viscosity, length squared per time. And the velocity itself, the result we're looking for, has dimensions of length over time. Okay, so we're looking for a formula like velocity equals some function of all of those other pieces, c, g, nu, and L. That's what a solution would look like. We would have a prediction of the velocity or speed based on these other parameters in the problem. And we can think of that as being something that looks a little bit like take c to some power times g to some other power times nu to some third power times length scale to some other power. And the only thing we know is that the dimensions of this thing had better be consistent with the dimensions of this thing. So the dimensions on this side are length over time. The dimensions on this side could be lots of different things. Well, it's going to be length over time raised to the a power plus length over time squared raised to the b power plus length squared over time raised to the c power plus length to the d power. So you can quickly see that not all possible choices of a, b, c, and d are going to give us something that has the units of length over time. That's what Buckingham's Pi tells us. How many possibilities are we expecting to find that would be dimensionally consistent with the result? So here's the key thing. Buckingham Pi tells us that for every parameter in the problem plus the number of results in the problem, which in this case is 1, 2, 3, 4 parameters, 1 result, 5 minus the fundamental d, how many fundamental units, and here the only fundamental dimensions we have are length and time, so we got 2 of those. So we have, in this problem, 4 plus 1 minus 2 equals 3 pi factors to consider. 3. Okay, so let's see what an example pi factor might be. 1 is u over c. We already talked about that one. That's the Mach number. So suppose this boat can go right up to the speed of sound and no faster, then we might say that the Mach number was equal to 1. That's the prediction for the speed. Forget all the other parameters. That's not what it is. But that's not going to be the most general solution, because we can imagine that the boat might go at some supersonic speeds, in which case the Mach number would just be one of the parameters that describes the speed that we go. Another one is UL over nu. We saw that one before. That's the Reynolds number. Suppose the boat goes up to a fixed Reynolds number and then can go no faster. Interesting. That would mean that instead of the speed of sound being the important physical parameter that limited the speed of the boat, it would be the viscosity of the water that's the important parameter that limits the boat. And then there's one more that's maybe not so familiar, and it depends on G. Okay, let's see. We want something that's dimensionless, like these two, U and U over G. So U over G has the units that is not dimensionless, because this is length per time and this is length per time squared. So let's take the square root of G, and we have length per time over square root of length over time. So we need one more G times L. Square root of G times L has the units of length squared per time squared, the square root of that, which is length per time. So this is also a dimensionless number. This one is called the Froude number. Okay, this one describes the speed of the boat versus the speed of the waves that are produced that are the same size as the boat. That's why it's the boat length that comes in here. For typical boats, for ones that are not going really fast and are what are called displacement hulls, that are pushing the water out of the way in front of them and they don't pop up and surf on top or anything like that, this is actually the critical parameter that governs the speed of the boat. And so how do we figure out a theory? So suppose we can neglect this one, then we would say, U is what a theory looks like. If you have only one important Buckingham parameter, then you would say it's the Froude number equals a constant. That's a key assumption, but if there's only one, that's pretty much the only kind of thing you can do that would be dimensionally consistent, is to say that there's only one thing that's going on. That thing, when the boat limits its speed, it goes to the Froude number equals a constant. And that means that U over square root of G L equals a constant, which means that U equals a constant times the square root of GL. So if the length of the boat gets bigger, so does the speed. If you're on a planet where gravity is bigger, the speed gets faster. Okay. What if you have more than one Buckingham parameter? What if we want to make some combination of the Froude and Reynolds and Mach number? Then we're back into this kind of a complicated setup. And so we might take this as the leading approximation. U equals a constant times the square root of GL times some function. We've already used F up there. Let's use G. No, let's not use G. Let's use function H, which is a function of the remaining parameters. Reynolds number, Mach number. So what this says is, here we got our original prediction that was something that was okay, and then we have something that is close to 1 when, say, the Reynolds number is maybe quite large, the Mach number is quite small, but if we went fast enough that either the Reynolds number or the Mach number got big, there might be a correction coming from this term to change this velocity to depend on multiple parameters altogether. That's the basic idea of how the Buckingham Pi theorem works.